Today we're creating a way for the user to communicate with the driver. This will allow the user to send data to the device as well as read data from it, but first we have to take a look at how devices are handled in Linux. You may have heard it, that Linux handles everything as a file. So files are files, of course, folders are files, mouses, printers, cameras, you guessed it, files. And our device will be represented as a file too. In the driver, we will override the read-write operation so that the driver will communicate with the device instead of reading or writing to some section of memory. Speaking of sections of memory, the kernel modules use separate memory space that is not accessible by user applications. It is called kernel space. Regular applications cannot read and write to it. It is unsafe in terms of security. The kernel provides special functions to transfer the data between those spaces. They are called copy to user and copy from user. The module would use them to exchange data with an application. Say, for example, we have requested a read from the device file. The module will have to generate the data it would like to output. It's a different story, but the data will be stored in the kernel space. The module will then have to copy this data into a buffer in the user space, and the contents of that buffer will be returned to the user as a result of the read operation. The write operation works similarly but reversed. The user leaves some data in the buffer in the user space and passes this buffer to the module. The module will then copy this data into its local kernel space variable and process it as it needs to. Probably send to the device, but it's a topic for later. So how do we create the files? Well, pretty simply. There is a function in the Linux API that does it, but it will need some information. It will need a name for a file, but more importantly, it will need a set of callbacks for events that happen to a file. So it will need a callback for when the file is opened, read from, written into, etc. All these callbacks are collected in a structure called file operations, or FOPS for short. Of those callbacks, we're most interested in the ones responsible for read-write operations. They provide a similar set of parameters, the number of bytes to read-write, a user space buffer to work with, and an offset. The read callback will need to write some information into the user space buffer. The write callback needs to fetch the data to write from the buffer. The offset is, well, the offset. If the user have requested a read of 10 bytes, but the function have returned only 6 bytes, the read operation will be called again automatically with the offset of 6 and count of 4, because there were remaining 4 bytes to read. The exception is when the function returns 0 byte, meaning there is no more data to read and the operation should not be called again. A couple more things to consider. Every device in Linux is assigned a number. Not only the USB devices, they have their own USB addresses. Every device in Linux has its own number. Actually, two numbers, called major and minor. Major number specifies one of broad categories of devices. We are not interested in that now. Minor number, however, is updated for every instance of the device. If we attached two of our custom USB devices, they would be assigned different minor numbers. Well, it would be handy if the device file had this number in its name, and it actually can have that number in the name. When creating the device file, the name we assign to it is actually a template. It may have a %d placeholder, which will be substituted by the device's minor number. You can see an example here on the slide. And the last one. In the code section, I will handle the user input as numbers, so we are supposed to only write numbers to the device. The module will have to be able to convert a string into a number, and the kernel has its own special function to do that. It's called kstr2l for kernel string to long. It works much like plain old A to I, but it takes one additional parameter called base. It allows the function to convert hexadecimal numbers from strings if the base is 16. If the user is supposed to only input decimal numbers, the base should be 10. That's all I have for now. I think we're good to go back to the IDE. Now we're ready to create a file so that the user can communicate with the driver. The function that does it is called USB register dev. It takes information about the device and information about the file, which we're about to create. Here I do quick error checking, and if it's okay, printing out the minor number assigned to the device. Creating a variable for the return value, defining a variable that will hold the information about the driver, giving it a name template, Afterwards, it will be passed through printf function, and the %d part will be substituted with the device's minor number. Setting its file operations field, I'm gonna define actual file ops now. For now, it will only hold callbacks for read and write operations. I am about to define those functions now. Let me quickly remind myself the prototypes of those functions. I'm searching for the definition of the file operations structure. There is a bunch of callbacks, I only need 2 of them at the moment. Changing their names to match the ones in the structure, printing out the number of bytes that was requested to be read. Now I need to give names to the parameters, the offset at which to start reading the file, the number of bytes to read, the user space buffer, and the pointer to the file structure, which is not important at the moment. This function returns the number of bytes that remains to be read, so if it's not 0, the function will be called again. This may cause the system to hang, so the function must return 0 at some point. Now I have to do the same to the write function. It will also print out the number of bytes that needs to be written. And contrary to the read function, this one returns the number of bytes that were written successfully, so if it returns less than the count, it will be called again. Now we're ready to build this. Removing the old driver just in case, inserting the fresh one. And yes, it looks like the device has been registered and have obtained number 2. We may check the existence of the file under /dev USB directory. Well, it's clearly not the right one. It turns out that the device was created right in the dev directory. Not sure why, I believe I had to use other function in order for it to go into the USB folder. Anyway, the file is there, let's try and read it. No such device. That's unfortunate. Will the file at least disappear when I remove the module? No, looks like it won't. It will cause problems if I try to read or write into this file as the module is unloaded, or if I try to create the same file again. That's why it's important to remove everything we've created and the device was attached. Specifically, this register dev call. It needs to be unregistered here in the disconnect function. I will also change the name of the file just to be safe. Now test it again. Okay, there is an error, probably wrong arguments provided to the register function. I suppose it's located in a USB-related directory since it has a USB in its name. Here it is. I provide the interface, I should also provide the driver structure, no problem. Back to my source, adding the driver structure, building the module again, loading the module, checking the files. The new one did not appear, I'll check the USB folder just in case. File is not there. Let's check the kernel log. I see the device registration has failed and the error seems to be 98. I guess I need to find out what this number means. I search for the register function to find out what it's doing. There is a couple of places where it might throw an error. I'll need to figure out their numbers. There is one list of errors, but 98 is not there. So back to the registration function, it must be throwing more errors. Here is another one, happens to be 98. Looks like the address is in use. I think it means that the minor number, the 2, is still assigned to non-existing module. I'm gonna fix it the easy way, restart my machine. So here is a freshly loaded system. I'm inserting the module again. Now verify that it's loaded. It is loaded with no errors, checking if the file is created. Yes, it is. Let's read it. I need to use sudo, and we're back to the no such device error. I'm gonna simply search for this message in the source code, remove the filter, try using quote marks, that's better. The first result suggests the actual error was e-no-dev, so we should search when this one is thrown. That's too many. Let's filter something more USB related, and inside the .c file. That's alright, I could handle this. Actually, I've looked through these files and I know that the right one is file.c here. So there is a function that has this return value by default, and if some file has a field called open, this value changes. I guess I know the problem. My file operations define read and write, but not open. Right here, just adding a new field. Now I have to find a prototype for this function, so I'm searching for the file operation structure again. Here it is. Now I have to give it the right name and give names to all the parameters. The function will return 0, meaning no error has happened. Now remove the old module build and insert the new one again. Except I forgot to build it. I'm gonna figure it out in a moment. Now load the module again and try to read the file. Well, something happened. Looking into the kernel log, there was a request for several thousands of bytes. That's okay, that's how the cat command works. Now let's try writing. I do echo write in the terminal. This method also works with regular text files, by the way. It did execute, now check the log. There was a request to write 3 bytes including new line, so it's working. I'm gonna read the file again just to make sure it was not a glitch. Well, now we want to show something on the screen when the file is read, don't we? So I'm gonna create a buffer that will be displayed. Initialize it with zeros and fill it with some values including new line. Now remember that buffer that was passed in the function. We need to copy the data into it. And I probably shouldn't give my buffer the same name. Anyway, this buffer is in the user space, that's why it's marked with this __ user thing. So I'll need to use this special function I was talking about in the theory section. Same thing with the write function. I will create a buffer to store the user input. The user input is going to be a number, so I'm creating a variable for a number as well. Now I have to copy the user input from the user space memory. Now converting the user input into a number with base 10 because it's decimal, not hex, and printing out the user input as well as the number it's been converted into. It's time to build this, and my compiler complains that I am not using the return values of the functions. I will create a variable to store the results. Not that I will use them, but it will get rid of the warning. Same thing for the read function. Build again and reinsert the module. Check the log, and we are ready to read the file. Nothing is shown, that's not good. What about writing? Well, something's happened. What does the log say? The log prints the number 33 including the new line and the 33 as a number, so writing is okay. Now I'm gonna do a little change while not recording, hang on. I've just added the number of bytes to the output and the terminal window has updated. The problem with reading is that the function returns 0 no matter what happens. Well, it means that the 0 bytes were read, so there is nothing to show, right? Well, we need to change that. The return value has to be the length of the internal buffer, but I can't hardcode this value either because it would mean that there are more bytes to read and the function will be called again. I will use some hacky fix here. The function will return a non-zero value only the first time it's been called. It's a not good solution, but it's simple and should work. Now try the whole build process again, but not after I fix some errors. Reinsert the module and read the file again. It says hi, that's a success. It does say hi only once, but that's okay. Now everything that's left is to send USB requests during these read and write commands.